Greetings, everybody. This is 7:30 a.m. Pacific time on February 25th, 2026. My name is Timur. You have Seth with me online today. Thank you for your interest in Mat3ra.com and welcome to our Mat3ra 2D webinar series. Here we highlight Mat3ra 2D, which is an open source code base to design and develop two-dimensional materials. As you can see on the next slide in Seth's presentation, slide number 2, Mat3ra 2D allows you to develop different kinds of material structures, starting from monolayers, going into defects, disorder, grain boundaries, and many other capabilities. Today is the 6th webinar in our series, and we will focus on reproducing publications that study point defects in multiple well-known peer-reviewed articles. Now let's go through the rules of engagement. Everybody who is present here today should be a registered Mat3ra user, but even if you're not, because everything we discuss is open source capability, you should be able to get access to it and utilize it even without being a Mat3ra user. If you want to ask questions at any point in time, please use either the chat functionality or the Q&A functionality of Zoom. We will have dedicated time to go through the questions at the end of the webinar, at the end of our discussion. All right. Now, without further ado, Seth, the floor is yours.
Greetings, everybody, and welcome to Mat3ra 2D webinar series. This is episode 6, where we are focusing on reproducing point defects from well-known publications. First, we're going to take a look at the presentation to give you an overview of our approach, and then we'll proceed to hands-on experience and creation of such defects. So one of the challenges in material science is that data used to train machine learning models is examples of simple 3D crystals, while for the applications in the real world, we need more complicated structures such as surfaces, defects, and interfaces. And we need a way to generate such materials. For that, we created an easy-to-use framework for the design of realistic 2D materials. Our approach has well-defined data structures to help organize information in a database and make it easier to build machine learning models. We demonstrate the application of our approach with a set of Jupyter notebooks that can be ran in any web browser. We primarily focus on 2D materials because this is the area that is important for electronics, batteries, and other developments, and the area is rapidly growing. Here we can see example of some of the structures that were created using our package. So grain boundary with passivation, intercalated interface, and other examples of the interfaces. Our implementation includes 5 components. First is the data standards housed in Mat3ra ASI package. It has different entities defined in the form of JSON schemas, and they define schemas for materials and other common physical concepts and operations. So when we say a slab and Miller index, it has one clear definition amongst the stack. The second portion is the commonly used examples data stored inside of Mat3ra standard data, which has examples of the entities adhering to the data standards from Mat3ra ASI. It's also available on GitHub and PyPI. Here we can see the list of materials with the names reflecting categories they belong to. And here's the example of the structural information for one particular material. We will be using some of the materials in today's recreation of structures from some data. Third one is generic code base inside of Mat3ra code. It has implementations of all of the entities inside of Python or JavaScript to make it possible to work with them inside of any software stack. This is used internally. We're not going to look at it closer today. But it is used inside of the fourth portion, which is the specific code base stored inside of Mat3ra made. This is the main package for the design of 2D materials. Primarily, it's written in Python, and it has implementations for main concepts such as material, its lattice, its basis, it has a set of functions to analyze, create a configuration, and to transform material. So it has analyzers and builders and configurations from which you can construct any complex material and create it. And the last step is to make the functionality available. We have provided code usage examples inside of Mat3ra API examples, which has a collection of Jupyter notebooks that are created in a self-documenting manner. So you can learn how to use Mat3ra made package by following a simple instruction. So, for example, if you want to passivate a slab, you would open the notebook that does that, see what properties are set, what functions are used, and how it operates. And also, you can use this as a practical tool where you can adjust properties as needed for your day-to-day work. And they naturally support collaboration because you can easily share, create your own notebooks, and edit across the team. The last stage is making functionality available to the user. We support running notebooks in any Python environment and IDE, such as JupyterLab, familiar to many. And we also allow for running inside of web-based Python runtime called PyDiet, so that those notebooks can be embedded in any web application. For example, if you're searching through our docs, you can see example of the tutorial, and then right there you can have the example notebook, which you can just run within seconds of its initialization without need to install anything or download anything. So it's nice to have something for fast iterations. And it allows for transformations with Mat3ra made, as well as PyMagen AC that are built here, built for this PyDiet and any pure Python package. Let's look at the implementation details. We devised an ontology for any transformation of the material, and we split the process of material creation into 3 parts: configuration, transformation, and then the final result. For example, if we want to create a slab, we would start with a bulk material, specify milli index, thickness, supercell size, and this is our configuration. Then we're going to use builder, slab builder in this case, apply it to configuration, which will yield a resulting material. And the metadata with parameters and all the transformations that occur to the bulk material are stored for provenance. Sometimes the structure you want to create is more complex and you don't know all of the properties for the configuration beforehand. For example, if you want to create an interface, you would need to define 2 slabs for surface and the film. And then you know the milli indexes, you know the thickness of each slab, but how do you you need to make those slabs coherent. For that, you need to find a supercell and the strain for the film. How do you do it? You define the slabs with the known parameters as before, and then you use some interface analyzer, for example, ZSL analyzer, with the parameter as max area, and then you apply it to the slab configurations, and you get the interface configuration. You get multiple interface configurations that are ranked by strain and size, and then you can select the one that suits best your needs, and then you can use interface builder, apply it to the configuration, and get resulting interface, which will be which will have the metadata, recorded all of the transformations and selections that occurred before. To make it easier to reason about materials and transformations and find the correct one, we devised such categorization of materials, where we start by dividing them into domains of pristine structures, such as ideal crystal, compound pristine structures, such as interface, defective structures, such as interstitial, and process structures, such as passivation. Further down, they divided by dimensionality. And at the end, we have final category, such as monolayer, nanowire, adatom, defect pair, or passivated surface. Some of them have variants. For example, how the structure was achieved. For interface, we might have ZSL or commensurate lattice algorithms. And recently, we've published a paper to archive M-code, materials categorization via ontology, dimensionality, and evolution, that explains in more details our approach and how we classify it, and how it's used to shortly encode any material that you have with M-code, which at a glance gives you condensed version of the categorization where it belongs to, so that we can later select specific tools that are needed for that particular type of material. And today we'll be focusing on defective structures, particularly zero-dimensional point defects. Before that, let's take a look at the quick recap of previous webinars, where we covered generic notebooks, in which each notebook is responsible for creation of specific material. For example, first part was focused on slabs and interfaces. Here we can see, to create a slab, we would start with a material that we get from STANdata. Then we use create slab function, provide parameters, and get the resulting material. For interface, we would define properties for each of the slab and use create slab function from the previous one for each of them, and then pass those materials to interface to create interface function and create the target material. So here is the example of two slabs and two different forms of interfaces that we've built. In webinar part 2, we looked at the nanostructures and heterostructures. For example, here's the example how to create a nanowire, where we again start with the material. We set parameters for radius, length, vacuum, and then we create a slab from which we cut the nanowire using some function, some mathematical function, and we filter by cylinder and get the final structure. The same goes for nanoribbon, where you specify the orientation and the size of it. And for heterostack, we get materials that compose it, define orientations and thickness for each of them, and then use various forms of interface analyzers to create interface between each next layer. And here's the example of structures that were created. So we have nanowires, nanoribbons, and the heterostructure of high gate material. In webinar part 3, we looked at the point surface defects, and this is point and surface defects, and some of the notebooks and functionalities will be used today. So to create a point defect, we create a material, maybe provide a supercell if we want to make it larger, specify defect configurations, and use create multiple defects tools function to create a final result. And then for example, for the island, we again create a material, create a slab, then we specify geometric function of the island that we want to create, and then we introduce the defect to the surface. And for the grain boundary, we get the material, specify two phases, properties of two phases, and create grain boundary. So here's the example of some of the point defects, surface defects, and grain boundaries. And webinar 4 was for disorder, perturbation, passivation, where we would use a nanoribbon from the previous webinar, find neighbors, find distances to nearest neighbor for each atom, specify the cutoff distance, specify what is considered to be under coordinated atom, and then passivate some of the bonds. The same we do for the nanowire here, and also the perturbation function, which in which we create a supercell of some monolayer or some 2D material, and then apply a function that transforms it to have a sine wave in X and Y in this case. So here's the example of some thermal disorder introduced into the interface, passivated surfaces, passivated edges of the nanoribbon and nanowire, and the structure of graphene with the perturbation. And now what we're going to cover today. We'll be using Materials Designer application and Jupyter Light transformation as before. We will create a set of materials from publications, and today we're focusing only on structures. Simulations will be added later in the next episodes. And today's focus is on the three examples: substitutional point defects in graphene, vacancy point defect in boron nitride, and the interstitial point defect in tin oxide. So the first one is where we are reproducing substitutional point defects in graphene from the paper by Yoshitaka Fujimoto et al. Formation, stabilities, and electronic properties of nitrogen defects in graphene. They focused, the key area of research was that nitrogen modifies electronic properties of graphene, and how it does it depends on the configuration of the defect. So for example, for the pristine graphene, the doping, most energetically favorable doping was for just simple substitution, where one atom was replaced by one carbon atom was replaced by the nitrogen. But with the vacancies present, the pyridine type configurations become more energetically favorable. And what's most importantly, for simple N doping, the N type conductivity is present. But when we have the vacancies and the nitrogens bind to the vacancy side, in that case, we have P-type conductivity. And also the trimerized pyridine, which example we see here, has introduced magnetic moment. And if we take a look at the paper, so we're trying to reproduce paper. What does it mean? We need to look at the paper and find the structures of interest. For example, here they have different structures of graphene with the defects, and we are interested in reproducing this one, the trimerized pyridine version. Here they discuss the energies and different effects that we see, and they specify that. So we need to extract the data for materials to reproduce. So we see it's a graphene. It has 4x4 supercell, which they mention, and we want to create a defect in some location, a vacancy defect, and then adjust the nitrogens. So when we extract this data, we should see that we need to get a graphene with the monolayer orientation, supercell size, and the positions of the relative positions of the defects that we found. Then the notebook then we're going to create a supercell and introduce defects using this function by providing different configurations. And we're going to set materials to the further research. So if we go ahead to Materials Designer Mat3ra.com. First, let's look at let's import Graphene from Standata. We can delete the silicon. And here we need to create, we need to find the coordinates for the defects. So if we use advanced supercell and we specify the 4x4, as was mentioned in the paper, we can have this structure that resembles what we had. And we, for example, want to create, we need to find the coordinate for the vacancy. So we can select measurements and copy coordinate function. And then if you want to create vacancy, we can click on the atom, and the coordinate is being displayed and is also being copied to your clipboard. So let me show then how we're going to use it. Now we go to View, Jupyter Light Session. Here we go to specific examples. And for point defect defect for substitution inside of Graphene. Here we can see that the notebook explains the paper, explains what the properties should be set, and here we specify supercell matrix to be 441, and we use Cartesian coordinates for the coordinates of the defects. And here we can see that we have coordinates predefined that were found this way. So we can specify the type of defect, get the coordinate from the structure, and also we use placement method of closest site so that any coordinate will be resolved to the closest site. So that's why in some of the instances here we have just not as fine coordinate specification because it's going to be resolved. Now, if we run all cells, we should introduce the all of the defects. So vacancy, substitutions, all be introduced to the material. Here, we're not going to be use this structure. It was just for the coordinates extraction. Here we're going to install the packages, and the materials will be loaded from Standata. But here we have example of loading from the folder in the uploads folder. And by default, we have some of the materials like nickel and graphene present in any Jupyter notebook for example, to use in case you don't have any other materials. So that's why we're getting graphene from there. It should be pre-visualized shortly. And after that, we're going to create point defect dictionaries for each of the defect. And based on the cell from on the top, and pass to the create multiple defects function, where we specify the supercell material and defect dictionaries. And then we're going to preview material, and it was saved to the computer, and we can see the resulting structure. Okay, next one will be reproducing vacancy point defects in boron nitrate. It's a paper by Fabian Bertoldo et al. Quantum point defects in 2D materials, the QPOD database. In this paper, they've investigated the electronic structure of point defects inside of multiple 2D materials. And here we're going to be focusing just on boron nitrate. This is interesting because some point defects can produce single photon emissions. at the room temperature. So this structure is interesting for the application in quantum computing for the qubit. They found that defect structure to get the correct. So the point defect of vacancy on boron location can have in-gap electronic states, and the particular configuration of it depends on the configuration of the symmetry of the nitrogens here. So to get the correct results, they needed to create this structure and relax it to the lowest configuration to accurately predict the charge transition levels. If we would open the paper to extract information, so here they discuss what they've been doing, and we need to get to the structure that we want to reproduce. So here they say that the inside of the in-gap electronic structures can be found, and to figure out which one exactly, you need to recreate the structure and relax to make to introduce the symmetry breaking into the vacancy defect. And they say that they need to create a large enough supercell to remove the symmetry for the correct computation. They say that they need to use 4x6 supercell, and with that information, we can go ahead and use the notebook to. With this information, we can go ahead and use notebook to recreate the structure. So again, the notebook is going to be structured as creating, finding the boron nitrate, creating supercell, and introducing point defects. And as a result, we should get the same structure that they have, less the relaxation. And it's very important to run the relaxation later for the correct predictions. So if you go ahead to Materials Designer and go to View Jupyter Light Session, the same drawer is going to be opened. And here, again, we go to specific examples. And point defect in vacancy in boron nitrate. Let me run all cells while I explain that we add the supercell of 6x2 to break the symmetry. And also we add some rotation, because a rotation of 90 degrees to have it oriented in the same way that the paper have. And for the vacancy, again, we defined the defect type and coordinate. In this case, it's in crystal coordinates, but it was found in a similar manner that we did for graphene, where we found the coordinate and then I think converted it to the crystal coordinates. Just you can look by looking at the structure, and since it's resolved to the closest site, we don't need to specify exact coordinate. It can be somewhere around here, around the nice numbers that you can remember, and it's going to be resolved to the correct coordinate, and the correct coordinate will be preserved inside of the metadata in the material. So here we create the supercell, we pass it to the create vacancy function, and then we preview the structure. If we toggle on bonds, we can see it more clearly. So it's the same structure that they have. Now, let's leave. Now it's the structure for. Next paper is the reproduction of interstitial point defects in tin oxide. The paper by Atsushi Togo, first principles calculations of native defects in tin monoxide. They've investigated the interesting effect of conductivity inside of the tin oxide, and they wanted to understand what's causing the conductivity. Two options were that the p-type conductivity that's shown originates from the vacancies in tin positions, and it switches and it creates a shallow acceptor sites at each of the vacancies. And the other effect was that the oxygen interstitial absorbs the lone pairs electrons of the tin atom and making it tetravalent. So they've wanted to know which of the what causes the conductivity. So if we go ahead and open the paper, we want to find the information for the materials that we want to recreate. We will be recreating one of the structures from here. So where we have the two defects, and particularly we'll start with the A option, which has vacancy in the tin place and the oxygen at the interstitial. This clearly looks like a repetition of 1 by 1 by 2 supercell with the atoms in the periodic boundary conditions visible. So we're going to use 2 by 2 by 2 supercell for this, but for some of the calculations they used 4 by 4 by 4 supercell. So depending on what structures you reproduce, you use different settings. So with that in mind, we can go okay, we extracted the information, and now we can go ahead to the same notebook and reproduce the structure. Again, the relaxation is important if you want to achieve the correct results. We can go ahead and go to JupyterLite session. Again, this is found in specific examples folder with the point defect interstitial inside of tin oxide. So here we're going to create a supercell of tin oxide, which we have inside of stand data, and we're going to provide defect configuration for vacancy and the interstitial. And the vacancy will be resolved to the closest site, and the interstitial will be using Voronoi tessellations to find the most appropriate position. So if we go ahead and run all cells, we should have the same cadence of installing the packages, because we reopen this every time. And then we'll get a material from stand data and create supercell, preview it, introduce the point defects, and using create multiple defects function, we're going to introduce them to the final structure. It should come out shortly. We can see that some of these, so the structures were saved to the computer, and we passed the one with the defect to the working stash. And again, here we can preview the materials. Bonds looks like it needs a bit larger chemical connectivity factor. Yeah, there we go. So tin is absent from here, so it's the vacancy, and then the oxygen was introduced in the at the Voronoi site. So, for example, if you want to create structure C, we would need to change the vacancy position. So here we can see that the vacancy is approximately, so it's the same 0 on the x-axis and 0.25 on the y-axis. So it looks like, from just if we're eyeballing, that we need to get some small relative position in crystal coordinates, and since it's going to be resolved to the closest site, we should get the correct position. Let's try this, and if we run all cells, we should see that we get the structure with the, okay, it was sent to the just a second. So it was sent to the main stash, and we can see, yes, that indeed we changed the position of vacancy, and the Voronoi oxygen was, and the oxygen was placed in the different position with the Voronoi tessellation. And we can do the same for different structures here, or different structures from the paper by introducing additional configurations for the defects. Now, if we get back, let me show you how you can access those notebooks. So we've already seen that the notebooks can be used inside of the Materials Designer web app. They are all embedded from this jupyterlight.mat3ra.com server. So from this path, you can access all of the notebooks that are inside of the made folder, which corresponds to the made package that we have. And here, if we open the introduction notebook, it's the familiar categorization of all the notebooks, and we can add any of the notebooks, open any of the notebooks. And here we have the specific examples, and you can open them and run them at the browser. And this was meant to be also accessed from documentation. So, for example, in Mat3ra documentation inside of tutorials. So if we go to tutorials, reproducing specific manuscripts, we have here an overview where we have the collection of all the specific examples that we have. So today we reviewed the, for example, interstitial point defects. We can open this tutorial, see the explanation for what we did today, how we found the coordinates, what we setting for the supercell, the different defects, etc. And at the bottom here, we should have the interactive Jupyter notebook, which we can enter as a full screen or just as a, we can we can run all cells and view and change anything. So it's the same Jupyter notebook as in the Materials Designer. So you can run it from the documentation to quickly see how it unfolds and adjust anything as needed. So we've introduced Mat3ra made package for the design of the materials. I showed how it can be used with the set of Jupyter notebooks in Mat3ra API examples. We shown that it can be accessed from jupyterlight.mat3ra.com, from inside of Materials Designer, and from the web app itself. And we will have a set of tutorials which show how to use it, and notebooks can be run interactively to see the functionality. All code is open source and available on GitHub and PyPI, and we welcome contributions. Next episode of the webinar will be on March 31st. We will be reproducing structures from publications, this time focusing on surface and linear defects. So all of the atoms, grain boundaries, islands, etc. Also, we are presenting on American Physical Society meeting on March 17, starting around 8:30, session F45 in the Colorado Convention Center. In case you're there, we encourage you to visit us and listen to the presentation. And later, we're going to have a happy hour at the 5430 rooftop at Denver, near the convention center, starting approximately from 5:30. So those that will be there, we encourage you to visit us, and drinks are on us. Now, back to you, Timur, and Q&As in case anybody has questions.
All right, just a quick Correction there, the next webinar will be on March 25th. That's the last Wednesday of next month, not on the 31st. Okay, let's open the floor to the audience's questions. Let's see if there were any questions in chat already. Feel free to raise a hand and ask questions directly if you like. Okay, I don't see any questions as of right now, so maybe let's talk a little bit about why you need to only have a single window open for Materials Designer. I think you've always had only one tab open for it and you closed all the other ones, right?
Oh, it wasn't for it's not for Materials Designer, it was for Jupyter Light transformation. So since this is the PyDiet that runs in the web browser, it's structured in a way that it has web worker that executes all of the code, and it's one per it's one per the browser, so you might have some interference in the work. So if we create some structures in one notebook, then it's just going to, the PyDiet kernel will be active. But if we have some other function, some other notebook opened, then in that case there might be some interference. For example, right now the PyDiet kernel says that it's unknown, although I'm selecting it. Maybe let me exit the full screen so that we can see. Here we have one notebook that's working, it's in the progress, and another one is unknown, and no matter what I do, it doesn't restart the kernel. Sometimes it does, but sometimes it has some interference within the same browser window. I think we can, yeah. So usually it's nice to have. It's one of the downsides of the PyDiet. It's fast to just open in the web browser and run, but sometimes if you have, for example, two of them open, one might get stuck and we have some interference. So this one looks like it's got stuck, but if we run, it should be faster. So it's important to see that the Python kernel is idle or active and it's present.
Okay, so as a rule of thumb, we should only have one single session open for the Jupyter Light. And then if you have trouble, then try opening it in a new incognito window where there is no cache, there is nothing that already is sitting in the browser from the past.
Yeah, so here we open some example. Yeah, so here it doesn't interfere with the main window.
Okay, since there are no questions yet, well, maybe let's take a look at how we can import arbitrary files. Let's say we don't have this information in some data yet. How do people import their own materials?
We can use, if we go to introduction notebook, here at the bottom we should have example from others import data. So we can import in any format that is supported by AEC. For example, also if you have some changes in the notebook, you can delete the notebook to make it reset, to make it be downloaded from the distribution so that you can clear up any changes that you made. So here we can see that the folder path is the uploads that's specified, and we can enforce some formats. I have a lot of materials, but for example, here we have some CIF files, some molecule files, and POSCAR. And if we run this notebook, we should get all of the materials, because we do not enforce the format. We should get all of the materials read in and displayed, and later they can be used inside the materials designer. So it says that it's failed to read some of the JSON files, so that are in our format, but it should read the, in this case, the AC, no, any structure that is supported by AC. So it gives you the list of all the formats. And again, here we had the molecule and CIF files for 2 of the structures, and they were they were passed to the material, to the materials designer. Looks like I had multiple of different molecules, and also they're saved to the this uploads folder as well by the set materials. So we read nickel Postgre, and now nickel JSON in our format was added here.
Okay, thanks for this explanation. So we have a question from Chandra, and it's about how to install Jupyter Lite along with Anaconda, whether we have to install that too. So Jupyter Lite is a browser native application, which means that you don't need to install it. All you have to do is to open a browser and go to jupyterlite.mat3ra.com. This is where you will be able to, once the website is loading, the whole environment is inside your browser already. That's the beauty and that's the convenience of getting started with this functionality. You don't need to install anything. Now, when you open a Mat3ra platform, Jupyter Lite is being loaded when you open the top level Jupyter environment. So if you click at the top and open the Jupyter Lite environment session, you can also access the same environment through this panel. So in each of these cases, again, Jupyter Lite doesn't need to be installed. It's just loaded inside the browser. It's also available through the Materials Designer interface inside the platform, as Vsevolod is now demonstrating. Lastly, maybe we should talk about how to use these notebooks inside Jupyter environment or Jupyter Lab environment. So if you do want to run it locally on your own computer, you should be able to do that, and Seth is going to demonstrate how now.
Yeah, so for example, we have the package, the API examples, that is available on PyPI and GitHub. And if we open in any, for example, in VS Code, then we should see notebooks. And here, in the other and materials designer, we have the notebooks available here, which is the same, for example, adapt and defect. And if we have the kernel selected, we can run the notebooks, and here we need to pass materials from the same uploads folder. So here we have by default nickel and nickel and graphene added, and I guess if I just add, let's see, it should get the some of the structures.
Before we get to run the notebook, let's explain how to get started once more. So we need to create a virtual environment, right? And inside that virtual environment, install the packages. Let's explain how to do that.
So we would need to create, in the API examples, we would need to create.
Let's start with a clean folder, and then create a virtual environment inside it, and install API examples. And I think that should be sufficient, right?
Just a second. Yeah, so we can have some folder. We can clone the, yeah, maybe actually let's do all of the. So if we go to API examples, you mean through clone or through API?
I think we can just create a virtual environment and install API examples from API. That should be sufficient.
Oh, okay, yeah, actually, yeah. So Python.
We recommend everybody work in a virtual environment instead of using Conda. It's just a bit more convenient. This way you can use Conda as well if you're used to that. So with Conda, you can set up a new environment, and otherwise it will be equivalent. So here you would source the environment and then do pip install Mat3ra API examples. And that package should include many of the dependencies that we've been discussing today. And I think it will include Jupyter Lab as well, right?
Jupyter Lab, maybe we would need to install separately, additionally. I just opened GitHub so that we can see that the README should state what we need to do.
Based on the README, I think it does include Jupyter. So if you like to run API examples locally, all you have to do is just set up a virtual environment and install Mat3ra API examples. Then if you open Jupyter Lab, it should be able to run on your local system. All right, let's see if there are any other questions. If not, then maybe we can talk a little bit about what will be present in the next few episodes of our webinar.
Next few. Well, next webinar will be reproducing the structures from the publications for the point defects. Next one will be on I think we can get to the calculations of the specific properties, for example, for band structures and total energies of some of the materials.
Right, so far we've been focusing on designing structures, and now in the next few episodes we'll be gradually transitioning to simulating those structures that we have just designed, and that's what we will be highlighting. And we have a set of different types of modeling techniques prepared to explain, starting from things like calculation of different energetic parameters like total energy, relaxation, formation energy, defect energies, and so on, and going into electronic structure, band structure calculations, going into vibrational spectra calculations, going into some sort of semiconductor specific, like valence band offset across interfaces, and then proceeding to chemistry and more sophisticated dynamics type of calculations. So we'll be highlighting all of that in the upcoming series. There was another question from Ahmad, and he asked us to highlight shortly how we can do a simple example in Mat3ra. So maybe let's take a look at the platform once more, and just demonstrate how to run a basic semiconductor band gap job. Let's go to example organization. Yeah. So this is the organizational profile that we use for demonstration purposes. It has multiple people working together inside a single account. And as you can see here, if you go to materials, we have a set of materials that we track, with silicon being, I believe, the default structure. Now, if we go to workflows, we can see the different kinds of simulation workflows that we track here, all different kinds. Let's try to create a job to demonstrate the basic flow. So if we go to jobs, we can click create, and it will preload using the default project, preload the job designer, where we have materials, workflow, and compute selection. We can just keep everything as is, or we can change and select a different workflow. For the purpose of this demonstration, we're just going to keep everything as is. And then in the compute section, we can select the cluster. You see, we support 3 major cloud providers, and then cluster 101 is where you can run calculations for free. That's the fundamental new capability. So we assume this will be mostly academics because this is public data. It will be feeding into a community, but let's keep with cluster 1 for now to keep everything as default. And let's save it and exit. Right, so now we have created the job, and the next step would be to submit it. If you click on run, it will get submitted. And then we use the debug queue there, so it should be able to start shortly. And when it does, it will show the results and the file stub with the information coming from this run. If we go back to the project level, we will be able to see when the job starts. It should happen momentarily. As you can see right now, it's in the submitted status. Depending on the load, it will transition as it did right now into the active status. And then during that active status, you can see the output of PWS CF unit in the real time. As you can see, this is a quick calculation, so it completes within a few seconds. And then the results are extracted and shown in the results on the file step. It needs to be refreshed there to see it, but it should be there momentarily. Okay. I think that should cover the simple example for Ahmad. Let us know if you have any other follow-ups. We can also take this discussion offline if you have any specific questions. All right. I don't think we have any other questions as of yet. With that, I think we've covered quite a bit. So we can wrap up for today. Thank you for joining us today, and we'll meet you again at the end of next month on March 25th, the last Wednesday of the month. If you are attending the Global Physics Summit in Denver, Colorado, United States this year, then please find us there. We'll be presenting on Tuesday, and we have a happy hour right next to Convention Center, as Seth mentioned before. Thanks, everybody. We'll see you next time. Bye.